Okay, starting off section 3.6 here. This is mainly just solving some different types of equations using a method called chunking, and it's really just factoring. So I'll try to point out how we can use chunking, think of it as factoring, and then solve some equations. For our first one, e to the 2x equals e to the x plus 6. The first thing I notice is that e to the 2x is really just e to the x squared, so it's something squared. So what I can think about is rewriting this as y squared equals y plus 6, where y is just e to the x. If I think of it like this, it's just a quadratic equation that I can set equal to 0, factor. So I'm thinking what multiplies to 6 and adds to -1. So that's -3 and 2. And then from here, for this product to be 0, y must either be 3 or -2. But y isn't really y, it's really e to the x. So then I finish this up by substituting e to the x back in for y and solving these two equations, because ultimately what I want are the x values that make this equation true. And here we get natural log of 3, and here that'd be natural log of -2, which hopefully you notice is no good, because we're not allowed to substitute negatives into natural logs. Similar idea here. I notice that 5 to the 2t is really just 5 to the t squared. So again, if I thought of y as 5 to the t, I'd have y squared minus 26y plus 25, and I'm solving a quadratic equation again. I'm thinking what multiplies to 25 and adds to 26, so that's -1 and -25. So y is 1 or y is 25. But y is not what I want, t is what I want. So substitute 5 to the t for y. And hopefully you can just look at these and tell what your solutions are. You get t equals 0, so 5 to the 0 is 1. T equals 2, so 5 to the 0. 5 squared is 25. Next up, we got the zero product property. We've been using this all along here when we solve an equation with factoring. Just want to point it out to you in maybe a different context. So we have these two factors whose product is 0. The only way for this entire value to be 0, the product of these two numbers, is if one of these is 0. So these are pretty straightforward solves, but we just think, well, either this factor x squared minus 3 is 0, or our factor 5x plus 8 is 0. It's the only way for that product to be 0. And then we just solve these separately. So x squared is 3, x is plus or minus root 3. And then here we got x is the opposite of this. Same idea for the second one. Set each factor equal to 0. Solve them separately. Here you get x squared is 5/4. So x is plus or minus the square root of 5/4, which you can simplify a little bit as plus or minus the square root of 5 over 2. And then here, this one is just 7/3. The last equation on the front there, this looks like a messy one. It's really not too bad. It's kind of the same process as before. Get this polynomial equal to 0. We'll try to factor it and then go from there. So moving all the terms to the left, you get x to the 6th plus 7x cubed minus 8 equals 0. This one I think fits best. If you just want to think of it as splitting the middle term, that's fine with me. The three-termed ones are almost always splitting the middle term. So I'm thinking what multiplies to negative 8 and adds to 7. Those are, what, 8 and negative 1. So I can rewrite this as x to the 6th plus 8x cubed minus x cubed minus 8 equals 0. Make sure you pay attention here. The 8x cubed minus 8x cubed should ultimately add to 7x cubed. It's kind of one way to check yourself as you're going through here. I'm then just going to look for common factors in the first two terms. You got x cubed. What's left after I factor that out? X cubed plus 8. I can bring out negative 1 from those last two terms. X cubed plus 8 is left. We're still equal to 0. So we've done most of the hard work here. We know we got this common factor of x cubed plus 8 left, so we know we're still in good shape. If we keep going, x cubed minus 1 times x cubed minus 8 is 0. Now it's 0 product property. X cubed minus 1 is 0, or x cubed minus 8 is 0. Here we get x cubed is 1, so x is 1. Here we get x cubed is 8, so x is 2. Section 7, Chapter 3 for pre-calculus is kind of your overall guide toward inequality solving using algebraic means. We're going to use the same strategies we did the other day, figuring out where our function would cross 0, or in other words, basically setting the inequality equal to 0, and then figuring out where our inequality does not exist. So if we can figure out those two places, remember that's the only way for a function to go from positive to negative or negative to positive. It has to either cross 0 or it has to jump it. The only way for it to cross 0 is if it equals 0. The only way for it to jump it is if it doesn't exist. So if I'm looking at our first inequality, 10 to the x squared is greater than 10 to the x plus 2. Logically, you can just kind of think to yourself here, well, the only way for this to be true is if the exponent of the 10 on the left side is greater than the exponent of the 10 on the other side. We know we can put any number into an exponent, so we don't have to worry about the case where x doesn't exist. So what I'm really trying to solve is x squared is greater than x plus 2. This looks a lot like a quadratic equation. It's pretty much the same thing. It's a quadratic inequality. You can solve it in mainly the same way. X squared minus x minus 2 is greater than 0. I can factor the quadratic. I'm thinking what multiplies to negative 2 and adds to negative 1. So that's x minus 2 and x plus 1. So really the only 2 points I'm interested in are at x equals 2 and x equals negative 1. And then I can test points on these intervals to see if that product would in fact be greater than 0. The way I like to do this is I like to think, is my factor positive or is my factor negative? Because if I know how many factors are positive and negative, I can figure out whether the product would be positive or negative. So I guess first we'll take care of these two possibilities. If x were negative 1, the product would be 0, and 0 is not greater than 0. So I'm just going to put a little x there. I can't include negative 1 in my final interval. If x were 2, the product would be 0. 0 is not greater than 0, so I'm not going to have that one either. Alright, so now I get to pick values on all these other intervals. So I think about a number less than negative 1, maybe negative 2. if I were to substitute -2 for x, I would get a negative factor here and a negative factor here. And then I'd think, okay, a negative times a negative is positive. Positive is greater than 0. That's a good interval for me. Any number less than -1 is going to satisfy my inequality. If I pick a number between -1 and 2, I like things easy, so I'm going to pick 0. 0 minus 2 is negative. 0 plus 1 is positive. A negative times a positive is negative. Therefore, not greater than 0. So that interval is no good. Any number between -1 and 2 will not satisfy my inequality. Lastly, we'll pick a number greater than 2, like 3. 3 minus 2, positive. 3 plus 1, positive. A positive times a positive is greater than 0. This tells me any number greater than 2 will satisfy my inequality. So, at the end of the day, what values will make this inequality true? Any number from -infinity to -1, and any number from 2 to infinity. Second one, I do basically the same thing. I'm going to set my inequality less than 0 or greater than 0, depending on which direction you want to move the terms. Factor it, find its zeros, make a number line, test points. So I'll do this pretty quickly. Feel free to pause it if I go too fast. I'm going to move these two terms to the right. So it's 0 greater than 15x squared minus 2x minus 8. Okay, so now this is a little tougher factor. I'm thinking what will multiply to 15 times -8, which is what, -120, and then add to -2, so that's -12 and 10. So I'd have 15x squared minus 12x plus 10x minus 8, again, checking to make sure your -2x would in fact be the sum of these two terms, and it is, so I'm okay, I think. Keep going. What's the common factors of the first two terms? I think we can bring out a 3 and an x. We'd have 5x minus 4 left. On these two terms, looks like we could pull out a 2. We'd have 5x minus 4. So now 0 is greater than 3x plus 2 times 5x minus 4. My key points are at -2/3 and at 4/5, because these are the zeros of those factors. I think we call those boundary points. So -2/3 and 4/5. I know neither of them are actually going to work because this is strictly greater than, 0 is strictly greater than, or my product is strictly less than. So these I know would make it 0. Make this factor 0. The product 0, excuse me, which is not less than 0. Testing a number less than -2/3, so maybe I choose -1. Our factor here would be negative, our factor here would be negative. That product is positive, which is not less than 0, so this one's no good. Picking 0 for this interval, this would be positive, negative, this product's negative, which is less than 0, so this one's good. Number greater than 4/5, maybe 1, positive, positive, product is positive, less than 0 it is not. So the proper interval that satisfies the original inequality is from negative 2/3 to 4/5. The next one down on the left side, throw in a little bit of logarithm here. Again, your process is the same. You just have to think about, in this case, where does log exist? We know we can only substitute positives into logarithms, so 0 is basically another boundary point here. We know we can't work a number less than 0 here. So right off the bat, I'm going to write that off to the side. I know 0 is going to be on my number line. So from here, let's just go ahead and solve it like before. We'll go ahead and set the inequality less than 0. I'm going to move them to the left. Factoring, it looks like you can bring out an x. Looks like you can bring out a log base 3. We're left with x minus 5. So then I can use zero product property to figure out the zeros of this this expression here on the left side. We got x equals 0 for him. Guess we already knew that. Log base 3 of x is 0, and x minus 5 is 0. Those are our three factors whose product we need to be less than 0. This one we already have. Log of 1 is always 0, so 1 satisfies this one, and 5 obviously is going to solve that last one. So my boundary points are 0, 1, and 5. Because this is strictly less than, I know none of these values that make this expression 0 are going to be any good. 0 is not less than 0. And if we substituted x, we'd get 0. If we substituted 1, we'd get 0. If we substituted 5, we'd get 0. If we think about values less than 0, well, we know we can't substitute them into the log anyway, so we know those are no good, because that would get ruined anytime we substituted it in there. How about values between 0 and 1, so maybe a half? So thinking about positive and negative factors again, if I substituted a half for x, that factor would be positive. The log would be negative. Log of a half is negative. You can substitute that in your calculator if you want to check. And then a half again, minus 5 is going to be negative. We have a positive times a negative, which is going to be positive, and that is not less than 0, so that's not in our interval. If we substitute a value between 1 and 5, so like 2. 2 is obviously positive. Log of 2 is positive. Again, you can check in your calculator if you want. And 2 minus 5 is negative. Positive times negative is negative. That's less than 0. That's a good one. And then one more. Value greater than 5. 5 is positive. Log of 5 is positive. Number greater than 5, 6. 6 minus 5, also positive. Positive times positive is not less than 0. So that's no good. Our solution is the values from 1 to 5. Any number from 1 to 5 will satisfy this inequality. The second one, a little easier, uses the same ideas, only we have less than or equal to now. The boundary points are pretty easy to see from the expression since it's already factored. 2/7 and 3/4. The difference here is because this is strictly, because it's less than or equal to, if we substitute 2/7, we will get 0 for this factor, making the product 0, and the inequality will be satisfied. So we'll include 2/7. Same thing is going to happen at 3/4. This factor would be 0. 0 times whatever that is still going to be 0, and that is less than or equal to 0. So 3/4 is good for us there too. Testing intervals again, same process, pick numbers, find if the factors are positive or negative. So I'm going to pick 0, negative, negative. Is that less than or equal to 0? No. Something between 2/7 and 3/4, so like a half. I substitute a half. Let's see, that looks like that's going to be positive. Yes, 7. Yeah, that'd be positive. 4 times a half gets you 2. 2 minus 3, that's negative. Positive times a negative is negative, which is less than or equal to 0. He's a good one. And maybe 1 here for the values greater than 3/4. 7 times 1 minus 2 is positive. 4 times 1 minus 3 is positive. A positive times positive is greater than 0, so it does not satisfy our inequality. And then since we need to include these boundary points, we'll use the bracket notation. Last two here, inequalities, and then these are just examples. If you think you know what you're doing, you can use this as a reference, but you don't need to keep watching. Again, I'm looking for boundary points. They're already set up pretty nicely for me because they're already greater than or less than 0. So I'm looking for where this function doesn't exist and where this function would equal 0. That's going to be really easy for you to find once you factor your numerator and your denominator. So in the numerator, I'm thinking what will multiply to negative 12 and add to negative 1, that'll be negative 4, positive 3. The denominator has a common factor of x, so I can bring him out. And then my boundary points are the zeros of all of these factors. So for x minus 4, that's 4. For x plus 3, that's negative 3. For x, that's just 0. And for x minus 1, that's 1. I think what I'd do next is just figure out if any of these are going to work. We know 0 and negative 1 are no good because those are going to make the denominator 0. Those are not going to work no matter what type of sign you have here. If this was greater than or equal to, then I would include the negative 3 and the 4, but since it's strictly greater than, these are not going to work either. Negative 3 and 4 make the numerator 0. 0 is not greater than 0, so again, I'm not going to include those. From here, it's just the same process as before. Test points on the intervals, figure out if the product would be positive or negative. I'd encourage you to do that. Don't type it in your calculator. There's a lot of calculations happening there that could go wrong. I think it's easier just to figure out if your factors are positive or negative. So maybe substitute negative 5, negative, 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 negative. That product would be positive, so that's good for us. Maybe negative 2, that'd be negative, that'd be positive, negative, negative. 3 negatives is going to be negative, which is not greater than 0. No good. Maybe number between 0 and 1, so like a half, would be be negative, that would be positive, that would be positive, and this would be negative. Two negatives multiplied is going to be positive, so that one works for us. 2 negative, positive, positive, positive. 1 negative is going to be negative, which is not greater than 0, so no good. And then maybe 5, positive, 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 positive. All these positives, product will be positive. So 4 greater than works. So we got a few intervals here. We got negative infinity, negative 3, we got 0 to 1, and we got 4 to infinity. As the values of x, that will make this inequality true. Process is nearly identical on the second one. Factor the numerator and the denominator, find your boundary points, test the boundary points, test intervals between, write your interval. So my boundary points are 0, negative 5, positive 3, and positive 2. Again, this one's strictly less than, so I know none of these boundary points are going to be part of my solution. The ones in the denominator are never going to work. The ones in the numerator would work if this was less than or equal to, but it is not. So now let's test intervals. Again, just think of whether the factor would be positive or negative. If I substitute negative 6, negative, 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 negative. 4 negatives is positive. Positive is not less than 0, so you're no good. Negative 3, negative, positive, negative, negative. 3 negatives as a product would be negative, and that's less than 0, so you're good. 0 to 2, so maybe 1, positive, positive, negative, negative. 2 negatives multiplied would be positive, which is not less than 0, so no good. Number between 2 and 3, 2.5. Positive, positive, negative, positive. 1 negative will be less than 0. And number greater than 3, they're all going to be positive. The product will be positive. That's not less than 0. So our intervals that work are for negative 5 to 0 and for 2 to